So we're going to make an adder circuit. So first, let's just design one for 2 bits. So like 1 column of addition. Because if I were to split a task of adding, I would do it column by column because that's the procedure I already use as a person. And it's the most logical way to split it up. So I'll try to design a circuit for 1 column of addition, and then hopefully I can use it for any column, right? Okay, so in a column I have 2 bits, plus I might have a carry bit, right? So let's say x1 will be the top row, so we'll be doing like x plus y and a carry. Okay, so we'll put x1 because this will be column 1. Okay? We'll have y1 and c. I'm going to put c0 because this carry came from a previous column if there was one. Okay? And then I'm going to have 2 outputs. What are the outputs? The outputs should be the digit at the bottom of the column and the carry for the next column. So I'm going to call that the sum bit and the next carry, which I'm going to call C1 because it came from column 1. Then these are my inputs, X, Y, and C0 are my inputs. So I can go ahead and fill them out like I normally do for binary. Since there are 3 of them, I have 8 rows in my truth table. And then I just have to figure out what happens for every single row when I do addition. So in the first case, I have all zeros. And that's easy. I know that adds up to be 0, and I don't have to carry anything either. If I have just 1, 1, as in the second and third rows, then I know my sum bit's going to be a 1, and I carry what?
0.
I carry a 0 in both of those cases.
How are you getting S and C1 again?
This is the digit that goes, if I'm doing this addition right here, that's the S, and this is the carry. So these are my outputs.
Okay, so you're just reading across. Okay.
So I'm reading it across. So I'm reading my values for X, Y, and C0, and then I'm pretending I'm plugging them into a column of addition, and what would be my digit that comes out would be S, and I would have to carry C1.
Okay.
So here I'm adding 0 plus 1 plus 1, and so that's 2, so I know my sum digit is going to be 0, and I have to carry a 1.
Right, okay.
In the next row, I have just 1 1, so my sum bit is a 1 and my carry is a 0. In the next 2, I have 2 1s, so that I know those are both 0, carry 1. And in the last case, I have 3 1s, which add up to 3, which is 1, carry a 1. So in this circuit, I have 3 inputs and I have 2 outputs. And I could make a chip and put all of these things on a chip and then hopefully have it manufactured. So anytime I had to do a column of addition, I could just plug this chip in. Okay? So we're the engineers. We have to design the chip. So we have to figure out what logic gates go on the chip. Okay? So that means that we have to write disjunctive normal form for each of these. Remember that? So for the S bit, let's write our disjunctive normal form for that. Let me zoom here. Oh, wrong way. So we have to write our min-terms for that. So S is equal to, it has a 1 where X1 is false, Y1 is false, and C0 is true. It has a 1 in the next case where X1 is false, Y1 is true, and C0 is false. It also has a 1 where X1 is true, and Y1 and C0 are false. And the last one, it has a 1 when all 3 of them are true. So I should have 4 min-terms because I have 4 1s in my column for S. And also, when I look at this, this should make sense in terms of what my sum bit is. You know it should be a 1 if exactly one of the inputs is a 1, right? So each of these first 3 terms has exactly one of the bits as a 1, and that makes me feel better, okay? And then in the last case, all 3 of them are 1s, and that feels okay too, because I know that then if all 3 of them are 1s, that makes a 3, which is 1 carry 1. So I just double-checked by knowing what I wanted. I just double-checked S to make sure that I wrote the right equation. Now I have to write one for C. Actually, let's go ahead and make a circuit for this. Okay, so if I had to make a circuit for this, I could write it directly, right? So if I was going to use multiple input gates, how many do I need?
2, 3, 4, 5. 5.
I need 1 for each of the minterms, right? And I can use a giant OR gate to OR all of them together. So I need 5 gates. So I'm making the gates for these, putting the knots on, and I skipped. Oh, I don't need 5 AND gates. I need a big OR gate here. So there's a circuit for S. And by the way, this whole problem is given in Chapter 9 in the Haggerty textbook, the little blue one. That's your textbook. Chapter 9 has an application section, and this entire problem is given in there. So this is without any reduction, right?
Yes.
So we could have reduced it and made a circuit for it, but that would have required more work. So just leave it the way it is. Now let's write a, has everyone finished looking at this? Yes? Okay. Now let's look at our carry bit and figure out when we need, what minterms we're going to need for that. So again, we have 4 1s in our column for C. Our first one is when X1 is false, and Y1 and C0 are true. And if you notice, we're going to have terms where 2 of the bits are 1s, right? Because we should have to carry if at least 2 of them are true. So when we have X1 is true, Y1 is false, and C0 is true, we have another one. Then we have a one where we have X1 is true, Y1 is true, and C0 is false. And in the final case, where all 3 of the variables are true. And again, I can double check that and see that in every case, 2 of the bits are true. And so I feel good because I know that that's when I need to do a carry, and there are no other times when I need to do a carry. So then as soon as I'm done with the minterms, we're ready to make a circuit for that. So I can just tell you how, if this were a homework problem, and you just wrote this circuit in disjunctive normal form using the minterms like we just did, it would be very easy for me to check the answer because I can just check and make sure that you have a not in the right positions on these gates. Because as I just said, we know that the carry bit is true when at least 2 of the bits are true. So all of these gates should have at least 2 of the bits true. All of these get ORed together to get my final output of C.